Okay, gang, let's begin. Your friend calls you up all the your so-called friend calls you up all the time and wants to come over to the house to see you, but you just say, hey, look, I'm really too busy. Calls again and again, and you say, I don't know what to say, but I'm just too busy. I'm just too busy with my work. They say over the phone, oh, that's too bad because I'm into giving massages and I have to do a 1-hour continuous massage. Massage? Well, maybe I can find the time. Come on over, right? So they come over and they give you a massage. And they pour some alcohol on your back. And when they pour the alcohol on your back, you go, oh, wow, it's cold. They say, no, it's not cold. I got it from the medicine cabinet, right where all the other stuff is. Is that alcohol colder than anything else in the room? No. If it were, what would happen? Thermal equilibrium, the other things would heat it up. Isn't that true? Doesn't heat flow from high to low temperature? And aren't all the things in our environment here, aren't this, all these things the same temperature? What if this book were hotter? What would it do to the table? Energy would cascade from the book to the table until they both became the same temperature, and then it would level off. So that alcohol that's poured in your back has the same temperature as anything else around. But it feels cold. And why does it feel cold, gang? Because what is that alcohol doing? What it's doing is what we're going to be talking about today. It's changing state. It's changing from the liquid state to the gaseous state, okay? And we call that what? Begin with EV. Evaporation, that's right. And we're going to be learning that evaporation is a cooling process. You know, sometimes you're swimming and you come out and you're all wet, a little breeze come by and, whoo, you feel kind of chilly. But if no breeze comes by, you don't feel so chilly. And what's going on? When that breeze comes by, what happens to the water in your body? It evaporates. When it evaporates, how does your body feel? Begin with a C. Cool. Now, we've got to ask the question, HC. Why is it that evaporation is a cooling process? And we can reason that out if we think small. See this glass of water here? Do you think all the water molecules in that glass are moving at the same speed all the time? How many say, oh yes, at exactly the same speed all the time? Stand up. Nobody. How many say, well, there's a whole distribution of speeds. And the average, that relates to that which we call temperature. Show of hands. Yeah, we got the idea. But you have all kinds of speeds in there, gang. You've got fast ones, you've got slow ones. You've got some at absolute zero at a moment. Boom. When it comes to a dead halt, boom, that corresponds to absolute zero. Next minute, something hits it, bam, bam, bam. They're moving all kinds of speeds. So you get a distribution of speeds. And a distribution goes something like this. It's like the distribution of our test scores. Remember how your test scores were? Score, number, no, here was a score here, and the number of people getting the score. Well, the same type thing here. This would be the temperature, or we could say the motion, or the kinetic energy. The kinetic energy of molecules in a glass of water versus the number of molecules. And what's the graph just say? That down here there's a few that are going slow, and there's a few that are going fast. These are relative ideas here, huh? Relative values. And most are going right about here in the middle. And when you talk about the temperature of the water, you're talking about the average kinetic energy, what most of these things are doing. Isn't that true? Now, which of those molecules do you think in a glass of water would be most apt to evaporate? The fast ones or the slow ones? I remember when I was a little kid, my father would drink his coffee and it would be too hot to drink. He's got to go to work quickly. And what he'd do is he'd take the coffee and he'd pour it in the saucer. He'd lift up the saucer and drink from that. Used to get my mother annoyed. She said it wasn't proper. What do you mean proper? He was using physics. Why did he pour it in the saucer to cool it, gang? Well, you don't be knowing. Well, it turns out evaporation is, guess what kind of phenomenon? Surface. The more surface, the more evaporation takes place. If I take a glass of water and set it here, it'd take a long time for you to see the level go down. If I take that glass of water and spread it over the top of the table, increase the surface, by the end of this lecture, that water would be, begin with a G. Gone, okay? It would evaporate because there'd be more surface. All my father did was increase the surface area. And when he increased the surface area, he gave what kind of molecules the chance to get out? Fast or slow? Fast. The fast ones leave. And when the fast ones go out into the vapor state, what's left behind? Relatively slow. And so your most energetic molecules are going to leave. And that's going to push the peak down. Because the slow ones won't have the fast ones to bump into anymore. And it's not like there are some that are always slow and some that are always fast. These are all water molecules, the same mass. So the slowest at one moment might be the fastest at the next moment. There's a continual chaos of motions in there. And it's completely random. Random that peaks out at some particular average. And when you take the faster moving and have them escape to the air, it stands to reason the slower moving are left behind. So thinking small, we can see why evaporation is a cooling process. This is one of the things that makes sense, yeah? Any questions on this? I saw a nice example of this when I was in India some years ago. I was in Khajuraho, India. It was really hot, like 110 Fahrenheit. And I was trudging through, and all these people were out in the field. They're all doing work out there, working in the field. In the corner of the field was a kid, a young kid, must be 8 years old or so. And that kid's job was to continually keep a great big clay pot of water cold. And how he did that is he had a gunny sack over the pot. The pot was open like this. He had a gunny sack over it, like burlap, yeah? And he had a little pot down here and a long stick with a gourd in there. And he would just keep making sure that the gunny sack stayed wet. And as long as he kept the gunny sack wet on that hot day, honeys, the water inside was begin with a C. And I ain't saying cool. Cold. H-C. Be checking your neighbor. See how that works, gang? See how that works? That gunny sack, water's evaporating, right? Which water? Which water molecules are evaporating? The fast or the slow? The fast. What's that leave behind? Slow. So the gunny sack then gets a little cooler than the outside. But the gunny sack is against the clay. And the gunny sack's a little cooler than the clay. Which way does energy go? From the clay pot to the gunny sack or the other way around? From the clay pot to the gunny sack. Heat flows from high temperature to low of itself, yeah? And so what happens, the gunny sack, the pot gives its energy to the gunny sack, and that keeps going off, off, off. You see what I'm saying? And so the pot gets cool, 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 but the pot's against the water inside. Now, if the pot's cooler than the water, and the pot's against the water, which way is the energy flow going to go, gang? From the water to the pot. And so you see, so long as he keeps having the fast-moving molecules leave on the outside, he's cooling the water on the inside. That's beautiful physics. Let me ask you a related question. Why do hot dogs pant? See a hot dog going like that all the time. All the time, get the tongue out. Why? Do you know why hot dogs pant? The answer's simple. No sweat. Dogs don't sweat. The only place dogs sweat are in between the toes. But in their body, they don't sweat. So they have to evaporate to cool. Where do they do that? Right inside where it counts. Right down through the bronchial tract. They're evaporating from the tongue and the mouth and right down through there. So they're getting a nice cooling. On a really hot day, that's why I see a dog going like that. Okay? Maybe trying to get the wind going through here. I'm kidding about that. Why do pigs wallow in the mud? He said, oh, that's because they're dirty creatures. Come on, why?
No sweat.
They want, again, no sweat, see? And they want to get wet. And how do they get wet? Get wet wherever they can. And they get wet, a little breeze come by, evaporation. Evaporation does what to them? Begin with a C. E, cools them. E. Nature's thermostat. Us, when you overwork, you guys start to sweat. Can I say sweat? All right, perspire. We start a little more refined, right? We perspire. And why do we perspire? Nature's thermostat. Isn't that true? Nature's thermostat. The harder you work, the more you tend to overheat, the more you sweat. And the more you sweat, the more you begin with EV. Evaporate. At least the perspiration in your body evaporates, yeah? And when that evaporation takes place, what's that do to the skin? Cool it or warm it?
Cool it.
Cool it. And so you feel cooler. Ain't that neat? I'll tell you where that short circuit's out. Do you ever stay in a hot tub too long? Yeah, it's bad. I remember way back in the 70s, man. It used to be common back there in San Francisco in the 70s to go hot tubbing. You guys, you meet someone new, you go to a movie or something, right? I remember one time, this lady, I asked her out, asked her to go to a movie. She says, why don't we just get to know each other better? Why don't we go to the Grand Central hot tubs? I don't know her yet, you know. My fondest dreams went a little bit too fast. Can I handle this, you know? This is a true story, by the way. And so, yeah, we went to the hot tub. Hey, I went to the hot tub, saw all my students here. Hey, what are you doing here? Hey, Mr. Hewitt, what are you doing here? Hey, that check your name routine worked, didn't it? Yeah, all right. But anyway, I got in the hot tub there. It's really, really hot, yeah? And I'm in there, and she's outside, and she says, Come on here, let's come over here. I'll give you a little rub down. Oh, I'll just stay in the water here a little longer. That water is hot. And that water is hot. And guess what I'm doing inside that tub? Sweating like mad. But the sweating usually it corresponds to begin with EV. Evaporation. And the evaporation usually cools you. But I'm in the water. And what's happening there, gang? Any cooling going on? No. So what does the old thermostat up here say? MS, MS, MS. More sweat, more sweat, more sweat. So I'm under the water, sweating, sweating, sweating profusely. My heart, boom, 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 boom. Overworking. I interrupted my body's natural function by getting in that hot water and preventing the evaporation doing the cooling. And honey, if you want to get wasted, talk about limp city. You will really get wasted if you stay in the hot tub too long. And you think sometimes people think, oh, you come out, hey, hey, man, hey. No, it's not that way. You come out, you're all wasted. You're all drained out. I wonder too about these deodorants. You know, you put these deodorants on that make it so you don't perspire. Can those be good for you? That means you got to overheat. If you prevent nature's function, sweating, you're going to overheat. And if you overheat, your heart overworks, and honey, you get wasted. Not energized, just the other way around. Kind of makes sense, huh? Hey, if evaporation is a cooling process, how about boiling? Oh, no, boiling wouldn't be a cooling process. Boiling's a heating process. Oh, no. Boiling's a cooling process. Don't believe it? You come home sometime, your hands are all hot and sticky, you want to cool them off? Your mom's over there cooking a great big pot of boiling water, ready to put some spaghetti in? You read in the book, boiling's a cooling process. What do? You take your hot and sticky hands and you dunk them in boiling water. You might say, what are you doing? I'm cooling them off. Good idea or bad idea? Bad idea. So is boiling really a cooling process? End with a P. Yep. Begin with a Y. Yep. The question is begged, what's heating and what's cooling? Tell your friends that when you're cooking some tea and you're boiling some water and they come by and say, what are you doing? Oh, I'm cooling off the water. They say, you're what? I say, I'm cooling off the water. And they look at it and they see all the bubbles coming out. You're cooling the water? Say, yeah, I'm cooling the water. Put your hand above. Ooh, I burned myself. You know why you burned yourself? You say, because heat came from the water. That's what I mean by cooling. See, I got the fire underneath. That's heating the water. That's the part that's heating the water. But the boiling process does what? Cools the water. Honey, the boiling takes away all the energy. To say you take energy from something is to say you cool it. If red hot lava is coming down the mountain and it cools, does that mean it's cold? No, but it's cooling as it's coming down. And your boiling water is cooling as it boils. Isn't that neat? That's why I use a pressure cooker. Use a pressure cooker to prevent the boiling. That will prevent the cooling, and that will allow you to get more heat, more internal energy in your water and cook your food faster. That's what it's all about. Because more pressure, let's look at that. Just regular boiling. Let's not look at the pressure cooker yet. I won't put the lid on, okay? This is just regular boiling. Let's use, what's the temperature at which water boils, gang? Is it 100 degrees Celsius? Is that right? Let's suppose we get to 98 degrees Celsius. Now the water molecules in the apple, they're going a lot faster than they were at 78 or like that. Isn't that true? Okay, now they're 98. Now those water molecules are all banging around there. A little group of them says, hey gang, let's cut out, let's form a little bubble, let's be buoyed to the top, and let's cut out. Let's steam it out right now. And so what they do is they form a little bubble here. And you know what happens when they form that little bubble? 30 kilometers of air, honey, 30 kilometers of air are squashing down, squash right down and smash that bubble right back down in smithereens. The air pressure outside is simply too intense to allow that bubble to form. Those molecules are going to have to go faster than that to exert enough pressure to overcome the pressure mainly of the atmosphere, let alone this height right here. So that's what happens. So the water then, since it's not cooling, the water goes up to 99. And the water molecules say, hey, let's try it again, gang. They cut out like this. And what happens? Whole atmosphere up above says, no, you don't. Smash. Smash them right back down. What happens? No cooling. The water heats up more. Now the molecules are more energetic, right? Will exert more pressure when they form a bubble, yeah? Now they form a bubble. Atmospheric pressure up above says, oh no you don't, smash. Old bubble says, oh yes we do, squash. Because now the bubbles are pushing out with enough pressure to overcome the atmospheric pressure plus the pressure of the water. And that's the temperature at which boiling takes place at sea level. Now you go up in the mountains where you're closer to the top of the air. Does the atmospheric pressure push as hard? No. So boiling should take place at a higher temperature or a lower temperature? Lower. Does it make sense, a lower temperature? Isn't that neat how physics makes sense like this? See? And if you keep taking the pressure away, pressure away, you'll get boiling at room temperature and below. There's a wonderful, wonderful experiment at the Exploratorium in San Francisco. It's my favorite. And all it is there's a cylinder, plexiglass, so you can see inside, and a vacuum pump. And you squirt a little water in a little cup. And you put the water in the cup at room temperature. You can even put your hand in everything. You close the thing. You throw the switch. Starts to take the air out. It starts to lower the pressure. And guess what the little water in the cup starts to do, gang? Begin with a B. Boil. And people walking by don't know what's going on. And they see the boiling water. And they ask questions like, gee, how are they heating it up? They're not heating it up. But it's boiling. The only time you ever see boiling when someone heating it up, honey, but there's boiling when you don't heat it up too. There's two things that go on with boiling. What are they? The heat you give and the pressure you exert. And if you change either one, you're going to change the temperature. You're going to change the temperature of the water, yeah? And so what happens? It's boiling, boiling, boiling. Now, here's the neat thing. It continues to boil. The pressure goes down, down, down. And you continue to watch, and lo and behold, turns to ice. Turns to ice. It's beautiful. The water boils right down to bubbles. You can even see the frozen bubbles. And the water boils until it becomes ice. So if you're ever with a friend that doesn't believe water's a boiling process, take him to the Exploratorium in San Francisco and check that one out.
Boiling's a cooling process?
Say again?
Boiling's a cooling process.
Boiling is a cooling process. What did I say?
Water's a boiling process.
Oh gosh, Mike. No. Oh, Hewitt. Yeah, yeah, water's a boiling. Okay. Thank you, Lee. Thank you. Yeah, but boiling really is a cooling process, okay? And when you're cooking water at home and it's boiling away, just recall people that, hey, what's the temperature of that water? And they say 100 degrees Celsius. You turn the flame up. What's the temperature now? Now, they say 100 degrees Celsius. That's right. Turn it all the way up. Really frothing over. What's the temperature now? They say 100 degrees Celsius. I know something, you know. I know the temperature of water is always the same. And then you say, well, how does it stay the same if I keep turning up the heat? And they say, well, gee, there's probably no reason for that. It's just a property of boiling water to always stay the same. And you say what? Check your neighbor. It makes sense, gang? It makes sense? We get the answer to such thing? Because the more heat you put in, the faster it cools, and one just offsets the other. And that's what keeps the temperature always the same. Really, really nice. Now, what happens if you put a cover on there? Some people say when you put a cover on top of your spaghetti that it will cook faster. True or false?
True.
The answer is true. Because when you put the cover on your spaghetti, you increase the pressure in here a little bit. Isn't that true? Doesn't the steam build up? And that's why the cover keeps popping up a little bit. But there's a little bit more than atmospheric pressure. So that's going to push down on the water more, and that's going to make the boiling temperature higher. So it might go up to something like, maybe, I'm just guessing now, maybe 102. Oh, incidentally, when you're cooking spaghetti, the recipes say this: bring the water to a rapid boil, and then put your spaghetti in. Why do they say that? Well, let me ask you a question. Will rapidly boiling water cook your food a little bit faster than just simmering water? And the answer begins with N. The answer is no. The temperature of the water is the factor that cooks your food. And simmering water with little bubbles, that's 100 degrees Celsius. Rapidly boiling water is 100 degrees Celsius. Now, why do the spaghetti types tell people to bring the water to a rapid boil? Any cook types here get an idea? Nobody got an idea. Lee got an idea.
The bubbles being on over on the spaghetti so
Yes.
it won't stick.
Right on, man. You're a cook, yeah?
No.
But you can do many things, and one of them is cooking, yeah?
No, I burn my food.
Say again?
I burn my food.
You burn your food, okay. But I bet you when you boil, you don't, yeah? All it is to keep the spaghetti moving. See, if it's rapidly boiling, it won't stick to the bottom of the pan. That's it, period. So if you want to save fuel on your fuel, bring it to a simmer, never mind the directions, and then just keep stirring it. Okay? Yeah. Anyway, over here, let's fasten this hood down, this lid down, like here. Let's fasten it right down. Get it so it's tight. And see this little valve here? Let's put some bubble gum in there and block up the leak, right? Okay. Now we put it in the stove and we cook it. What do we call it? Begin with a B, end with a B. Bomb. That's a bomb, gang. Because you know what's going to happen? that pressure going to build up. It's going to keep getting hotter, hotter, hotter. Then finally explode. So you have to have that little safety valve. And how much is going to come out depends on how much weight you're going to put on there. You can put different value. This squashes down so hard. This squashes down harder. I'm not really sure how this works. But I think these things block off the amount of steam that can come out of there. And so finally, you'll build it up to a certain pressure in there. And when you've got a high, high pressure, you might bring that thing up to something like 120 degrees. Maybe it'll take 120 before it starts to form steam. You see what I'm saying? Now, 120, I mean, the steam is built up in there, but it's pushing down so hard that it's preventing all these little bubbles from forming. So the water heats up. Honey, you're going to cook your potatoes very quickly in that water. How about the converse? You go up in the mountains and you just have a regular pan like this, and you're going to cook some boiled eggs, okay? And usually you put an egg in there and you leave it for 3 minutes, yeah, at sea level. Now you go to the top of the mountains, you put it in it for 3 minutes. You take your boiled egg, you open it up, yuck, feathers and everything. The thing is raw. You got a raw egg. Why you got a raw egg? Because the water wasn't hot enough to cook it. It probably was boiling at 90 degrees, something like that. So the temperature of boiling water depends upon the pressure that's exerted on the water. It makes sense, yeah? Common sense stuff. Hey, that's the beauty of physics, yeah? Okay, evaporation is a cooling process. How about the converse, condensation, when water molecules condense and form a liquid, when vapor goes to liquid state? Just use reason. If evaporation is a cooling process, what would condensation be? A heating process, a warming process. In fact, a lot of time, if you're in a cold climate, you're taking a shower, and you put the shower off, because all of a sudden the telephone rings on the other side of the house, and you go streaking through the house, and then you feel cold out there. Do you know why you feel cold out there? You're all wet, and what's happening to your body? You're evaporating, and it's cooling. And so you want to feel warmer, so what do? You come back, and you jump back in the shower stall, you close the door or close the curtain, and you're right there, and it turns out the temperature of that shower might be the same as outside. But you feel warmer in the shower. Anyone have an idea why? Well, there's something going on there, and it's not evaporation, and it begins with a C. Condensation, gang, yeah, condensation. And what's happening is all that water vapor, bam, bam, is coming, tattooing on you, banging in you, clanging on you, giving up its energy to you, and how do you feel? You feel warmer. And if in that shower, that condensation just exactly equals the evaporation, then you feel perfectly comfortable with no net change. Usually both processes happen. I mean, on a muggy day, that's a day when you're perspiring and you're evaporating. But condensation of the surrounding atmosphere is happening at a greater rate than the evaporation, so you feel hot and sticky. So on a muggy day is accompanied by a warming day, because when that water condenses, it gives up its energy and warms up the air. Kind of neat. Any question about that? Lee.
When water vapor condenses in the air, the surrounding air temperature goes up.
Yes.
And how does the vapor release this energy to the air? How does the air know to warm up when the water vapor condenses in the air?
Okay, we said evaporation is a cooling process, and condensation is a warming process. How does the air know to warm up? What's the mechanism for that? Let's take a look at that. I think I can show you that, Lee. Let's look at evaporation a little closer first. Evaporation, we have these molecules in here, huh? Here's the surface of some water. Here's a water molecule here moving with a high kinetic energy. A high kinetic energy right against that one. This one's got a low kinetic energy at this moment. These two have a total energy that adds up to something. What happens is high kinetic energy boom, hits this. This one then knocks out, and this has the high kinetic energy, and this one over here then has a small kinetic energy. Can you kind of see that? The total energy is the same as before and after. But now out here, most of the high kinetic energy is out in the atmosphere and the low is left behind. So that's evaporation as a cooling process. Lee, your question is the opposite one. What happens when the air molecules, when molecules in the air slow down and condense? First of all, we got to understand something. Which water molecules do you think would be most prone to condense in the air? Fast or slow? Slow. Let me give you an example. See this piece of fly paper? Okay. Now a fly is going to come down and hit the paper. But high kinetic energy. Watch this. See that fly bounce right off? Did you guys see that? Again. Bounce right off. It's got a lot of energy. Boom, bounce right, a lot of momentum. Boom, right off. Here's a slow-moving fly. It gets stuck. Guess what behaves the same way? Begin with M with molecules. Especially H2O molecules, because water molecules tend to stick to each other. They do that by electrical forces, something we'll be talking about soon. But there's a tendency for water molecules to stick. You know why the water molecules in this room right now don't condense all over the place? Because they're moving more than 15,000 kilometers per hour. And these things are hitting, boom, bounding off so fast, boom, they stay in the vapor state. But if you slow them down, they'll condense. So let's get back to Lee's question. Here we have a couple of molecules. Kinetic energy, another molecule. Let's suppose this H2O. Kinetic energy, moving toward each other. Add these two kinetic energies, you get a particular value. Can these energies transfer? If I have a couple of pool balls, can I have one pool ball come in, boom, slow down, this one speed up? And the energy before and the energies after always the same? Guess what behave the same way? Begins with M. Molecules, okay? Let's suppose these things collide and boom, this one here takes off with a high kinetic energy. Then the water molecule rebound with only a little kinetic energy, such that this plus this add up to be this and this. Can happen? Now when this does happen, and the one with a low kinetic energy happens to be H2O, and it's near a neighbor that just did the same thing, that made some other oxygen or nitrogen molecule go faster and give up its energy and gets over to here, these H2Os will coalesce and then become, and more and more happen. What happens here, this becomes a little droplet. It's not part of the air anymore. There's your condensation. What is left behind? The air is warmer. Can you see that? So in the last bounce of an H2O with an air molecule, the last bounce that gives up most of its energy to this one, and then they coalesce, that last bounce energy warms up the air. This happens even when it's snowing, especially when it's snowing. One time I'm with my friends up at Lake Tahoe, and I'm up at the top of the mountain. And all of a sudden I feel it really, really getting warm. And I'm just kidding around. I go like this: "Humba, humba, humba, snow, snow, snow." And someone said, "Hewitt, you're taking yourself too seriously." And all of a sudden, "Hewitt, son of a gun, I estimated you, man." And the snow is all, how did I know it was going to snow? The same type thing. That air got noticeably warmer. So in changes of state, you get an energy transfer. And I think we have a diagram in the book that looks something like this. Okay, you go from the solid to liquid. Does it take energy to make it go from solid to liquid, or give off energy? Let's suppose the substance is H2O. It's an easy one to remember. Ice, water, steam. You go from ice to water, it's going to have to take in energy, right? You'll have to put energy into the H2O. And if you want to turn liquid to gas, say water to steam, you got to keep putting the fire in, yeah? So you get energy in going this way. But how about the converse? That's the part we're talking about now. How about you go from a gas to a liquid? Does the gas give up energy or take it in? It gives it up. And how about going from a liquid to a solid? Does it give it up or take it in? It gives it up. And so you go like that. And this is energy out. It used to be, before the time of electricity, a lot of farmers would get wiped out in the northern parts of America when their food would freeze. They'd have these canning cellars that would be down below 6 feet level, but sometimes it would get so cold that the darn food would freeze, it would be in jars, and they would be wiped out. You know why they'd be wiped out? Because it turns out when those jars of food freeze, it turns to ice, and the ice does what? Begin with an X. Expands, and it makes the glass begin with a BR, break, and the food is WO, wiped out, okay? And the farmers feel UH, unhappy. And that's because they don't know their F, physics, okay? Let's look and see what's going on, what some of the farmers found out they could do. To prevent that from happening, some farmers would put down a great big tub of water right in the middle where all their cans of food are all arranged. And they keep the liquid water there, okay? Now, so long as they keep that liquid water there and that water starts to freeze and turns to ice, and before it's solid ice, put some more water there, honey, they're not going to have that canning cellar get below 0 degrees. Can you be seeing why? Because it turns out the water is turning to what? Ice. When the water does that, what's it do?
Releases energy.
It's like the farmer says to his friend, "Hey, Joe, come on over here and see the radiator I got. I got a radiator down in my canning cellar. When it gets really cold, this radiator is going to give out heat and keep my crops from going below 0. And so the neighbor comes over and comes down the stairs, blah, blah, blah. "Hey, Joe, where's your radiator? I don't see any. All I see is this tub of water." He says, "That's the radiator." "That's no radiator." He says, "Put your hand in that water and tell me what you feel." "Well, I feel water in the liquid state." "What do you mean the liquid state?" "Well, the molecules are moving around with enough energy so they don't bond to one another." "Enough what?" "Energy," right? He says, "Okay, what happens that liquid water turns to ice? Where does the energy go?" "Oh, nowhere. It just sort of," come on, gang, where does it go? Where does it go? It gives it to the surrounding air. And as the ice freezes, it heats up the air, and it keeps that air at a nice steady 0. Just like your water boiling stays at 100 all the time, in this, you'll keep your air at 0 degrees. And your crops aren't going to freeze at 0. You know why? You could get sugar and salt in those jars. And that sugar and salt will lower the freezing point to below 0. And so the only thing that would freeze at 0 is the stuff in that can, that big pot, or other jars of water. But the jars of water all have sugar, salt, so they're okay. And this is a case where change of state. You go this way, you get energy out. That energy will help you. Go this way, energy in. A friend just got burned. You say, "Oh my God, I don't know if he got burned with steam or boiling water, but they're both the same temperature, so the burns must be the same." What do you say? "Honey, they're not the same. Because if it was a steam burn, I don't want to hear it was a steam burn. If it was a steam burn, that steam burn gave up what when it became water? Begin with an E. Energy. And if that energy happened to be more than the little cells are held together with, and his hand's all blistered and 3rd-degree burn. So that's what happens. There'll be, when a change of state is accompanied always by an energy transfer. You go from solid gas to liquid, energy out, liquid to solid, energy out, and go liquid to liquid, energy in, blah, blah, blah. It's just kind of like, air conditioners work this way. You got an air conditioner in your house, right? What's it doing? Energy taken in or energy given out? You can make it operate both ways. You could take the air conditioner, and by the way, you would never take your air conditioner and put it on the coffee table and turn it on, would you? That's like opening the refrigerator door on a hot day to make the room cool down. Do you ever hear anyone doing that? You walk in, they get the fridge door open. "What are you doing?" "I want to get cold." It won't work. In fact, the room even gets warmer. Do you guys know why? What would you have to do to make the room really colder with the fridge door open? You'd have to stick the condensation coils outside, because you've got evaporation coils on the inside and condensation coils on the outside. In the condensation coils, what's happening there? Taking in energy or giving it off? Giving it off. And that's why you put your hand in the back of the fridge, honey. It's warm. Isn't that true? So if you got, and then the motor, of course, it makes the whole thing go and will even give you a net heat increase than if you didn't do anything. So you got to put one side on the outside. So you got your air conditioner out there and you're feeling frustrated because all of a sudden it gets winter. Just take it around, flip, turn it around, and now you got a heater. Air condition the outside out, and you'll get heat inside the house. And that's why air conditioners will run both ways, but you don't have to take the whole machine out and turn it around. There's a little switch that'll do it for you. So all they do is just exchange heat from one place to another. How? By the change of state of liquids that easily change state from one to the other, usually Freon. School day. You walk in, your favorite bar, and you get a drink. Do they serve beer in this kind of glass, this kind of glass, or this kind of glass? You guys be too young to know about this sort of thing. But let me just be telling you, most bar rooms will serve beer in this kind of glass. Do you know why?
Oh, evaporate.
CH. That's why. This kind of glass here, if that's with cold beer, what's the outside of the glass going to be? It'll be wet.
Yeah.
What happened you get beer in a glass like this? And you're a little bit sauced, and you're holding a glass. Hey, let's toast it, boom, down on the floor.
Yeah. Oh,
Glass like this? Or if you do have a glass that you have a handle like that.
Yeah.
In Germany, they're like that, okay? But without the handle, they're going to slip out. This one here just slip right through your fingers. This one here starts to slip through the fingers, and even if you're sauced, you'll still kind of grab it and hold it. So they're shaped like this. Also, they'll also give you a little napkin on the bottom, right? What's the little napkin for? You say to the waitress, "Hey, what's the napkin for?" She says, CH, 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 CH. Don't you know your physics? Why the napkin? Because this stuff is going to start to pour down. I can remember when I was a little kid, I still remember this, my father used to drink a lot of beer. And he didn't want me to drink his beer. And I reached over and I took the edge, because I saw the edge was all wet. And I could take the edge and I tasted. Didn't have any taste. I thought the beer was leaking through the glass, you see? And I was at the edge because it was all wet. The glass get wet, yeah? And I remember putting my hand inside. Ew, yucko! Why does Dad drink that? You guys remember that, like Listerine or something, you know? Okay? But anyway, it's that wetness on the outside. And I never said to my dad, "Hey, Dad, how come it's wet on the outside?" My dad would have said, CH, son, CH. Right? We don't be knowing that. Or do you take a glass and make little rings like this? On top of the table, like that? Whenever you put it down? In fact, a little stain. That's why you got to put the pledge and all that stuff on this. You don't get those stains, yeah? Okay. Why do you get those little rings? CH.
Condensation.
Why do we get, oh, sometimes you're out there parking with your friends. You're parking, you're kind of steaming it up, and the car's closed and everything, and the windows are getting all wet, okay? And your sweetheart says, "How come the window's all wet?" And you say what? CH, CH. And the friends say, "What means CH?" And you say what? Condensation, honey, condensation, honey. That's what it is, it's condensation. How about clouds in the sky? How do you suppose you get the clouds? Little kid look up and say, "The beautiful cloud." "Hey, wow, look at the beautiful clouds. How come the beautiful clouds?" What do I usually say to a kid when the kid says that? "Shut up, kid, shut up. Don't ask questions like that." No, you're destroying an Einstein or a Mozart or something. What do you say to the kid? CH, CH, condensate. It's condensing up there. Remember we talked about the warm air rises? What if that warm air got a lot of water vapor? When that rises, what's it do? Begin with an X. Expand. When it expands, what's it do? Begin with a C. Cools. To say it cools is to say it slows down. To say it slows down, say the water molecules can what? Begin with a C. Condense. And when it condenses, what do you get? Begin with a C. A cloud. Can you see that? Yeah. And usually the clouds around here, right over the mountains, isn't that true? And why is that true? Let's look at that. It's Hawaii, huh? In fact, you can always tell when you're flying toward Hawaii if you want to get to. Just look out the window and you see all the clouds. There's Hawaii. Always clouds up here. Most always. Out here? Sometimes. But most always up here. Why? Because the air, boom, it's like hitting the spoiler of your car, right? Boom, it gets bounded up, right? When the air goes up, What's it do? Begin with an X. Expands. When it expands, what's it do? Begin with a C. Cools. When it cools, what's it do? Begin with a C. Condenses. And that condensation forms what? Begin with a C. And if it happens at sea level, what do you call it? Fog. Fog, that's right. But these updrafts give rise to those clouds. And that's kind of nice. That's kind of nice. I remember I used to prospect for uranium out in Colorado. And I didn't know my physics then. And we used to be in the San Luis Valley and go up to the Sangre de Cristo mountain range, and that's where we had some uranium claims. And we'd drive up there all the time, and there'd always be clouds right over the mountain peaks. And you get up there, and it's cold and damp and everything, and out in the valley it's dry. And I used to wonder, that's all mixed up. Why aren't the clouds over here where the farmers need them? Who needs them up there? I never knew why the clouds preferred to be near the mountain, as if the cloud was an entity in itself, looking for a place to go, you know? And I didn't know about these things then. But all this is that the air coming across the valley, water moisture, there they are, generated right up there. So that's nice. On islands with mountains, people there can then have water to drink. I got a question for you. Here's an island in the middle of the Pacific. It's just a great big sandbar. No elevation. What's the chances of having clouds up above there? And you want to drink water down here?
Same as
High or low? Check your neighbor. How many still say you have a high chance of getting clouds up there? Show of hands. Ooh, nobody. I tell you what, gang, over that land, you're going to be getting clouds. Because there's going to be updrafts. When the sun be beaten down on the water, and then beaten down on the sand, which is going to get hotter, gang?
the sand.
The sand. The sand for two reasons. One thing, the water is transparent, and all that energy is diluted through a whole lot of water. The sand, the top part's going to catch it. Another thing, the water get a high specific heat. Take a lot of energy to change the temperature of the water. That sand is going to get hot. You might be in the water, cool, put your foot in the sand, boom, it's hot. That gets very hot. So the air above here is very, very warm. It becomes less dense. Buoyed up, cooler air comes in. And so the air rises up. And what does nature give that island? Clouds. What's the reason for the clouds, gang? Because of warm updrafts. The air goes up, the air expands. So when the air expands, it cools, condenses, clouds. CCC. Neato? Turns out, when air rises and expands, it cools by about 10 degrees Celsius for every kilometer. The converse is true, too. If the air all of a sudden nosedived down, it would heat up 10 degrees for every kilometer. There are parts of the world where in the middle of the winter, the air sometimes is abnormally warm. And what happens is cold mountain air nosedives down into the communities. And when it nosedives, what's it do, gang? Expand or compress? It compresses. And what compresses, does it cool or heat? Heats. And that can heat up the whole community. Some of these are called Chinooks, winds, which go up over a mountain, give off their moisture, and come back down and compress, and become abnormally warm and heat up the whole community. So if you compress air, you heat it. If you expand air, you cool it. Kinda neat. I got a question for you. If you go about 5 kilometers above Hawaii right now, let's say it's 0 degrees Celsius, freezing, 5 kilometers high. And 5 kilometers high up there, you have a great big dry cleaner's bag, a great big huge baggie, filled with that 0 degree air. And that baggie is up there floating like a balloon, yeah? But it's got a rope on it. And you take that rope and you put it on a winch, and you pull that baggie down quick. Whoo! When that baggie gets to the bottom, will it be 0 degrees? What will its temperature be? Think about that. That's physics. Later.